High AP Chemistry. This is your first lesson on Unit 12 Acid-Base buffers. This corresponds to the Day 81 assignment. Okay, so let's talk about a strong acid reaction. The first 10 slides or so are a review of some concepts from acids and bases. So this is a strong acid reaction. So you're putting hydrochloric acid into water, and that's going to produce hydronium ions, H3O+, and chloride ion, Cl-, which is the conjugate base of HCl acid. And conjugate base and conjugate acids are brother-sister, and the difference is one proton between them. You'll see the significance of that when we learn how to construct a buffer. Also, H3O+, that's what defines a solution as being acidic, is how many of those H3O+ hydronium ions are in the solution. That's just simply the definition of an acid, how much H3O+ it has. Okay, so the question says we're going to start with 0.4 molar concentration of HCl. So what the problem tells you is what you're going to put in the top line of that, or the second line actually, of that rice table, the initial line. So you always start, everything in the question is going to be up there. So it says we're going to start with 0.4 molar concentration of HCl. You never include water. You don't ever include in these pure solid or pure liquid. Why that is, you don't have to concern yourself with. Just remember that it is. And since it doesn't give us concentrations, initial concentrations of hydronium or the chloride, then you just assume that there's zero. That's always fair to do in these types of problems if they're not given to you. Okay, now this is where the algebra comes in. We're going to have some sort of change. We don't know what it is, minus x. Generally, we don't know what it is. But we're going to say it's minus 1x, because the 1 comes from the coefficient in front of HCl, which is 1. And almost always the coefficients in acid-base reactions are 1. So it's minus x. It's minus because it's decreasing. The concentration of the hydrochloric acid is going to be decreasing. On the product side, over on the right, it's plus x, because there's a 1 in front of H3O+, that's the coefficient, and it's increasing. It has to. It started at 0. It has nowhere to go but up, so it's going to be increasing. And the same with the chloride ion, okay, and that's a plus x as well. Now, here's the thing. The point of this exercise is that if it's a strong acid, we know that it's going to totally dissociate, 100% go from reactants on the left to products on the right. So we don't really even need to do this algebra. Instead, you say all of that HCl is going to be used up, and you're going to end up with, you have HCl 0.4 molar. So what you're going to end up with after it's broken up is 0.4 molar of the H3O+ and 0.4 molar of the Cl-. Okay? You have one thing, it's going to break into two things, but you're going to have the same amounts of those two things on the right-hand side, 0.4, 0.4. So now when we simply add or subtract as appropriate here, you get a 0. You have no HCl left at the end of the reaction. It's not even called an equilibrium reaction. In fact, it's erroneous to have that double arrow there. It should be a one-way arrow from left to right. You're going to end up with 0.4 molar of the H3O and 0.4 molar of the Cl-. So in other words, with a strong acid reaction, or the same is true of a strong base reaction, if you're told you're starting off with 0.4 molar of the acid, you know that's going to all go away at the end, and you're going to have 0.4 molar of the products on the right side. So it all dissociates into 0.4 molar, 0.4 molar. So a strong acid goes from 100% reactants to 100% products. And since 100% of a strong acid dissociates to form H3O+, there's no need for a rice table when you're using a strong acid. You just know, as soon as you read that question, 0.4 molar HCl, okay, that's going to produce, usually you're interested in the hydronium ion concentration, that's going to produce 0.4 molar of H3O+. And that's, you just see that automatically. You don't need to set up a rice table for a strong acid or a strong base. Okay, now we're going to do a weak acid. Now, weak acid is one that doesn't totally dissociate. And that means it's going to go, it's a reaction that's not going to go all the way from reactants on the left to products on the right. It's going to go somewhere in between and then come to a stop. And so the purpose of these problems, this is where you need a rice table, is to figure out what those concentrations are. So we're given this information. We're going to use acetic acid, CH3COOH. We're going to start at a 2.1 molar concentration, and the Ka of acetic acid is 1.8 times 10 to the minus 5. The bigger the Ka value, the more it will dissociate. The smaller, the less it will dissociate. Ka value, if you remember from the acid-base unit, is the intrinsic strength of the acid. So strong acids always have a higher Ka value than weak acids, because if you take equal amounts of a strong acid and a weak acid and put them in water, the strong acid will produce more hydronium ions than the weak acid. So given equal amounts, so it tells you how strong that acid is. The analogy I used back in the acid-base section was if you had a 12th grader who could lift 10 boxes up onto a shelf and a 6th grader who could lift 5 boxes up onto the shelf, then you would say that intrinsically one 12th grader is stronger than one 6th grader. But pH of the solution is dependent not only on how strong each of the acids is, but how much of them you use. If you had only one 12th grader lifting boxes onto the shelf, but you had 100 6th graders, the 6th graders could lift more boxes up on the shelf than the one 12th grader. And what that indicates, it's not just a matter of how strong each individual is, it's how many you have. So a solution can be more acidic if you put a whole lot of a weak acid in as compared to only a small amount of a strong acid. But K value is telling you if you had equal amounts, just say 1 molar of each, which one would be stronger. And equal amounts, the strong acid is going to be stronger than the weak acid. Okay, so let's set up the Rice table. There it is. So step 1, complete the reaction with the acid donating a proton to water to create H3O+, and enter the initial concentrations of each reactant. Okay, so again, we're going to fill out the top line. So we start with acetic acid, CH3COOH, at 2.1. It does not give us any initial concentrations of H3O+ or the acetate ion, that's the CH3COO-. So those are going to be 0. Again, don't use water, don't include water, and that's going to be 0 and 0. Now we are going to need to do the algebra here because it's not, all that 2.1 is not going to go away and turn into 2.1 of hydronium and acetate over on the right. So we're going to subtract some number x. Since no concentration values, okay, of H3OCl+, we can assume they're 0. So now we're going to enter a variable on the change line. So the coefficient of acetic acid there is 1, so it's going to be minus 1x. It's decreasing because it's a reactant. It's going down in value. And then on the right side for the products, it's going to be plus 1x for hydronium and plus 1x for the acetate ion. So they have coefficients of 1, and they're going up because they're increasing in concentration as the problem goes on. At least until it reaches equilibrium, and then they come to a stop. Okay, now you simply do an addition or subtraction problem. 2.1 minus, there's a negative sign, yeah, and there we go, read that. Coefficients in front of x variables are the same as in front of the reactants and products in the reaction above. Now 2.1 minus 1.x is that, and then 0 plus x is x, 0 plus x is x. Okay, now we write the law of mass action, sometimes just called the equilibrium equation for the reaction, and there it is. It's the Ka value, which we know, times the products on the top, H3O plus times acetate ion, concentration of H3O plus times concentration of acetate ion. Remember that in that formula, the exponents of each of those concentrations is the coefficient. So the coefficient in front of H3O plus is 1, so the exponent H3O plus to the first power, so you don't need to write that, and CH3COO minus to the first power, so you don't have to write that. So you don't have to write the exponents, but remember there are exponents there, you just don't see them. Okay, and then on the bottom you have the reactant, that's the CH3COOH. So now we can substitute in numbers and our algebra variables. So Ka equals that, so there you go. There's the Ka, and the products on the right, x times x, and on the bottom is the reactant, 2.1 minus x. Now you can use the simplifying assumption that states that the value of x is much smaller than the initial concentration, 2.1 molar, then x in the x minus 2.1 can be eliminated. Okay, it's so small compared to 2.1 you can just ignore it. It just doesn't change the value very much. And that's true in pretty much every problem we do. You can go ahead and assume that in every problem that we do here, but you should use the 5% rule at the end to verify that. Okay, so the assumption must be justified at the end of the problem using the 5% rule. So there's the formula. And we can just change that to x squared on the top, x times x, and on the bottom we eliminated that x. 2.1 minus some tiny number effectively equals 2.1. So now we solve for x. So there's the equation we had on the last slide. You multiply top of both sides by 2.1, you cancel, and you get 3.78 times 10 to the negative fifth equals x squared. Now we take the square root of both sides, and you come up with x equals 6.15 times 10 to the negative 3. So that's what x equals. So what is x? We go back to our Rice table, and we're only looking at the equilibrium line now. That's where we are. This is at equilibrium. So x is the hydronium ion concentration, H3O+, because that's what the bottom, the equilibrium line of the Rice table says. It's also the concentration of the acetate ion, CH3COO-. And then if you want the concentration of the acetic acid over there on the left, it's 2.1 minus x. But 2.1 minus 6.15 times 10 to the negative 3 is a very small change. So, but we'll go ahead and do that on the next slide. So calculate the concentrations. You might be interested in only one, and usually it's the H3O+. You want to know how acidic the solution is. Okay, so there we did figure out for the acetic acid, and it's 2.1 minus 6.15 times 10 to the minus 3, which is very, very tiny. I come up with 2.09. I could have rounded that back to 2.1 actually. So it would have essentially been the same answer, and that's why you eliminated the x in the first place, because it didn't change the amount of COOH. Very little of the COOH broke up, dissociated, and turned into those products on the right. Okay, and then for H3O+, it's simply x equals 6.15 times 10 to the negative third. Same with the, it says Cl-, that's a typo. It's the acetate ion there, CH3COOH. Okay, now we're going to go ahead, just as the exercise, we're going to calculate the OH concentration, the pH, and the POH concentration. For this, you should have your acid-base roadmap, and it shows you what the formulas for those are, but we'll just come down here and do it. So for the OH, there's a formula on the acid-base roadmap that says the hydronium H3O+ times the hydroxide OH- multiplied together, assuming 25 degrees, and if they don't state a temperature, you can just assume that, is 10 to the negative 14th. So that means you're going to divide 10 to the negative 14th by the hydronium ion concentration that we calculated on the last slide, and that gives you a hydroxide concentration of 1.6 times 10 to the negative 12. Very, very small number, because this is really an acidic concentration. It doesn't have very much hydroxide, very much base in it. Okay, for the pH, the formula is simply the negative log of the hydronium ion concentration. So that would be negative log of the number we came up with on the last slide, and you do that on your calculator, you come up with 2.2. That's getting to be a pretty strong acid, not what you would call a strong acid, but 0 is the strongest possible acid. Generally, strong acids are 1.5 and below, so 0 to 1.5. This is 2.2. So for a weak acid, it's pretty strong, but it's still a weak acid. Finally, the POH, and again, there's a formula on the acid-base roadmap. Please print that out. POH plus pH equals 14, so we just figured out the pH. So that means 14 minus 2.2 is 11.8, and that's the POH of this solution. Okay, now we're going to move on and get into some concepts that we need to have to know how to build a buffer. So, in the acid-base section, we dealt with acids reacting with water. When the proton from the hydrochloric acid is dissociated from its acid, it leaves behind the chloride ion. A negatively charged ion can attract H+ hydronium ion, making it a base, making the chloride ion a base. So what remains behind is a negatively charged chloride ion, Cl-. The hydronium ion, in the absence of any other substances, that's the H+, attaches to a lone pair of a water molecule to become H3O+. So remember, either H plus or H3O plus can both be called a hydronium ion and can be represented in a chemical equation. I prefer we use H3O plus because that's actually chemically what it is. It's a water molecule with an extra proton attached. A base that differs from its acid by exactly one proton is called a conjugate base. So hydrochloric acid, HCl, and the chloride ion, Cl-, are conjugate acid-base pairs. Think of them as like brother and sister. Strong acids completely dissociate in water. This means that every strong acid molecule that enters water will give a proton to a water molecule. So if we drop the hydrochloric acid into water, that proton moves over there. That was a hydrogen atom, which was a proton and an electron, but it left the electron behind on the chloride. That's why the chloride ion now has a negative charge. And the proton alone jumped over to the water molecule. Okay, in the acid-base section, we dealt with acids reacting with water. It is possible for an acid to react with a base other than water. So sodium hydroxide is a strong base. It completely dissociates into Na plus and OH minus when it goes into water. So we drop it into the water, and that sodium comes off. Remember, sodium from your solubility rules always dissociates no matter what it's with. So it came off. Now it's going to go down and sit off on the side. It's a spectator ion. It just watches. It doesn't recombine with anything, so it doesn't play any further role in this chemical reaction. So what you now have there is a water molecule on the bottom over on the right and a hydroxide molecule, an OH minus, on the top. Now we're going to drop our hydrochloric acid into the pool here. So hydrochloric acid is now in the water along with a hydroxide ion and a water molecule. Now we know before what we've just learned about strong acids that hydroxide will normally 100% of the time give up that proton to a water molecule. 100%. It loves to give up protons to water molecules. But now the water molecule has a competitor, that hydroxide ion. So the question is, which of those two would the proton rather go to? The water molecule, we know it likes to go to water molecules, or the hydroxide. Okay, so the answer to that question is it goes to the hydroxide. The water molecule has a negative dipole on the oxygen side, but it is not as strong as a hydroxide ion, which is a full 1- charge. So an ion is a full charge. It's either 1-, 1+, 2-, 2+. In this case, hydroxide is a 1-. The water molecule, remember, is still an electrically neutral molecule. It just has one side that's a little more negative and one side that's a little more positive. But if you compare the strength of each of those, the hydroxide is much more negative and therefore much stronger at pulling a positively charged proton. And what you see happens here is the proton will be attracted to the OH minus hydroxide over the water molecule. But look at what it formed. When it drew that proton away from hydrochloric acid, it jumped on the hydroxide, and now what you have is another water molecule. Nature loves to make water. That's why it's the most common substance on Earth. So when you put a hydroxide, which is characteristic of a base, and a hydronium ion, just the H+, which is characteristic of an acid, you put them together, you have a water molecule. So when the H+ attaches to the OH-, it forms a water molecule. Water is a neutral substance. The pH is 7. It's right in the middle of the pH scale. This is called a neutralization reaction because you took an acid, which is acidic, obviously, and a base, which is basic. You put them together, and now you have neither an acid nor a base. You have a neutral substance, which is what water is. Acids and bases can neutralize each other so that a solution is neither acidic or basic. Okay, now we're going to see what happens when we put a weak acid into the water. So we have a bunch of water molecules there. So hydrofluoric acid is a weak acid because it is not one of the 7 strong acids that you were asked to memorize. So if it's not one of the 7 strong acids, it's got to be a weak acid. Okay, when we put hydrofluoric acid in water, only a small fraction of the molecules will dissociate and pass the protons to water molecules. So they jump in the pool, the hydrofluoric acid, and HF does not completely dissociate. This is the definition of a weak acid. In this example, we will say that 1 out of 4 HF molecules ionizes and passes a proton to water. The actual number for HF is much less than this, but we're just trying to keep the numbers small and simple here. So we'll say it's 1 out of 4. So that means that proton jumped over to a water molecule. The other 3 HF molecules do not ionize at this time. Okay, so you had 1 out of 4 ionize, 3 out of 4 didn't ionize in water. Why is that? Because the fluorine is just better at hanging on to those hydrogens than was, say, chloride or chlorine. In chlorine, all of the hydrogens jumped over to the water molecule. That made it a strong acid. In this case, just some of them do. That's because the fluorine does a better job of hanging on to that proton. So remember, dynamic equilibrium means that the ionized HF can take back the proton and any of the other HFs can pass the proton to the water. In other words, it's 1 out of 4, but it's not always the same 1 out of 4. That proton can jump back to that fluoride ion, then one of the other protons can jump over to another water molecule and then go back and go back. But on average, at any one time, it's 1 out of 4. So just as a weak acid HF can neutralize, okay, I'm sorry, that's just a mistaken sense. In this example, we will say that 1 out of 4 HF molecules ionizes and passes a proton to water. And there we see it. The other 3 molecules do not ionize at this time, and again, that's the same slide. That's a duplicate slide. Okay, same concept, so you got to hear it twice. All right. There we go. Now we're going to move. Okay, here we will place the weak acid HF in a solution with a strong base, the sodium hydroxide NaOH. Now keep in mind, there's still far more water molecules than there are of either the hydrofluoric acid or the sodium hydroxide. Far more. But we're going to put some sodium hydroxide NaOH into the solution. So how many of the HF molecules will dissociate in this solution? Well, the first thing that has to happen is those sodiums have to come off. They dissociate completely. That's just from our solubility rules. They will break off from anything. So now you're left with the hydroxides. Now the hydrofluoric acid jumps in the pool. Now the question asked was how many of those protons on the hydrofluoric acid will jump over to the hydroxide ion. Remember, for water, it was only 1 out of 4. But now we're not dealing with water. We're dealing with hydroxide, an ion. So how many do you think? Well, the answer is all of them. Hydroxide really pulls strong on those protons. So for a weak acid, if it's in the presence of hydroxide ions, it acts like a strong acid. It totally gives up its protons. That's only to hydroxides for a weak acid. Okay, strong acid gives them up to anything. A strong acid would give up all of its protons to hydroxide as well. We saw that earlier. So in the presence of hydroxide, the protons on the hydrofluoric acid or the weak acid will completely dissociate. This means that every strong or weak acid molecule that enters water will give a proton to a hydroxide molecule. It really should be hydroxide ion. Okay, let's talk about salts. What is a salt? A salt is a neutralized acid or base. An acid can be neutralized when the 1+ charged hydronium ion, that proton, on it is replaced by a 1+ cation element. So what does that mean? So remember from when we were talking about ionic bonds, how the elements in the first column, and we'll just take lithium, sodium, and potassium over on the left side of the periodic table, they like to ionize by giving up 1 electron, because 1 electron meant they had the electron configuration of the noble gas in the row before it, and so they like to be +1 charges. if you just simply look at your sheet 60 common ions, or the other one, the charge numbers of ions periodic table, you'll see that everything in the first row is a 1 plus. So a 1 plus is the charge on those elements when they ionize. It's also the charge on a proton. A proton is a 1 plus. A proton has a 1 plus charge. So when an HF weak acid molecule dissociates, it produces its conjugate base, a fluoride ion, F-. This is a reversible reaction so that the fluoride F- base can take back the same proton or a different one. So remember, reversible reaction, that proton can leave, it can come back. That's not true of a strong acid. Strong acid, the proton leaves, it's gone forever. It can never come back. But here it can come back if it wants to. So fluoride ion, F-, conjugate base of hydrofluoric acid. Okay, so a salt is a neutralized acid or base. A salt is formed when a 1 plus cation, such as sodium, Na+, attaches to the conjugate base of HF or some other weak acid. So in this case, we just saw the proton go away, become a hydronium ion, and the fluoride ion is sitting there negatively charged. So what we can do is take our ion, our cation, our sodium cation, and it can replace that positive proton because they both have the same charge. A proton and the sodium ion have the same charge. So this can come over here. So the Na+ and the F- form an electrically neutral ionic bond. NaF is called a basic salt because it is formed from the neutralization of a base. So what you did is you took an acid, you took that +1 charged proton away from it, and then you replaced it with some element other than a proton. A proton's not an element, but some element that also has a +1 charge. And now it's neutral. It no longer has a positive or negative charge. That NaF is electrically neutral, and so it no longer acts as either an acid or a base, and that's called being neutralized. Okay, so that takes care of some of the essentials that you need for Friday when we start talking about how to construct buffers. Is the concept of a weak acid, a weak base, conjugate bases, and conjugate acid-base pairs, and salts. What a salt is, you're going to need to know that as well. Okay, so that takes care of this lesson. Go ahead and answer. There's 7 questions. Some of them require a little bit of explanation to them, and go ahead and try to get that done by Friday, and we'll see you then. Have a good day.